Hi. Today we're going to talk about the fifth and final gas law that you guys need to know about, and that is the ideal gas law. Okay? Now, the ideal gas law is basically an equation that relates all of the properties of an ideal gas. And remember, an ideal gas is a model that we use to understand the gas laws, and it is basically a model where it is all gases behave exactly the same. They behave like this ideal hypothetical gas, all right? At least under most normal conditions. And we'll talk later about when it doesn't behave like that. But the ideal gas law basically says, well, since all gases behave the same under the same conditions, if you know most of the conditions, you should be able to then calculate the final unknown condition. All right. And if you remember, there were four variables: pressure, volume, temperature, and the number of moles. And basically, using this formula, if you know any three of those conditions, you can calculate what the final one is. Okay. So it relates all four of the gas variables. Now, the formula is PV equals nRT. Now, four of those variables you guys already know. P is pressure, V is volume, N is number of moles, and T is temperature. But R, what's R? It's the pirate constant, R. No, sorry. It is the universal gas constant, all right? And it is basically the ratio, that's where the R comes from. It is the ratio of how the other ones relate to each other. Now, it has a very specific number, okay, 0.0821. That is the numerical ratio. But of equal importance are the units. Now, it looks a little weird. This is a compound unit, all right? It's kind of like miles per hour, but this has two things on top and two things on the bottom. So it's a fraction unit. On top, you have liters and atmospheres. And on the bottom, you have moles and kelvins. Now, if you remember, I told you rule number one, units must match. Well, in the previous gas laws where you had changes in conditions, we had we stated that the units of the initial conditions had to match the units of the final conditions, right? So like if P1 is in atmospheres, P2 must also be in atmospheres, sort of concept. Well, in this, since there's no initial or final conditions, instead, the rule applies to these units. Now, these are the units that all the other variables have to be in before you can plug in the numbers, okay? So in other words, volume has to be in liters, temperature must be in kelvins, pressure must be in atmospheres, and amount must be in moles, all right? So these are the units that all of the variables have to be converted to. There's no choice in this one, all right? So you want to make sure that all of these are converted to match the units of R. Also, please note that on the test and worksheets and so forth, I'm not going to tell you this is an ideal gas law problem or this is a combined gas law problem or whatever. Part of the skill that you're learning is to look at a problem and figure out what gas law to use. Well, as you know, since all the other gas laws are part of the combined gas law, and then you have the ideal gas law, which is separate, the trick to knowing which one of those two main ones to use is right here. The ideal gas law is the only one that involves moles, okay? So if you see anything having to do with amount or moles, that means that it is that it is going to be using the ideal gas law, okay? If there's no moles, then you use the combined gas law. And remember, basically for this, I'm going to give you three of the variables, and you need to solve for the fourth, all right? And that is it. So make sure you also look at the sample problem video for ideal gas law to see how these are all put together and solved. So this sample problem is for the ideal gas law. I can tell it's ideal gas law, other than the fact that it says it, because the problem involves moles. All ideal gas law problems involve moles. Now, the question reads, what volume is occupied by 0.250 moles of carbon dioxide gas at 25 degrees Celsius and 371 torr? Using my chemistry reference sheet, I see the ideal gas law is PV equals nRT. So I list out each variable, P, V, N, R, and T. P is for pressure, so that's the 371 torr. V is for volume, and that's our unknown. N is the amount, so that's 0.250 moles. R is the universal gas constant, which, according to my sheet, is 0.0821 liters times atmospheres over mole kelvins. So 0.0821 liter atmospheres per mole kelvins. And then temperature is 25 degrees Celsius. Now, the trick with the ideal gas law problems is that they need to be all having the correct units. The units must match those of the universal gas constant. Volume must be in liters. Pressure must be in atmospheres. Amount must be in moles. And temperature must be in kelvins. Now, pressure is in torr. That needs to be in atmospheres. So we have to convert it. Now, the pressure conversions say that 1 atmosphere is equal to 760 torr. Since I'm starting with torr, I draw a small grid. I put the 760 torr on the bottom, and the 1 atmosphere goes on top. 371 divided by 760 equals 488 atmospheres. 3 significant figures, 3 significant figures. Now, temperature must also be in kelvins. So I do that by adding the 273, and I get 298 Kelvin. Now, the formula, once again, is PV equals nRT. I have to isolate the unknown of V while it's still in letter form. To isolate it, it needs to be all by itself on the same side of the equation and a numerator. Now, V is already a numerator, but it's being multiplied by P. So I want to do the opposite of multiplication, which is division. That way the P's cancel out, leaving V all by itself. But of course, what I do to one side, I have to do to the other to maintain balance. So volume is equal to N times R times T divided by P. So, plugging in the correct numbers, N is 0.250 moles, R is 0.0821 liter atmospheres over mole kelvins, and T is 298 Kelvin. 298 Kelvin. All divided by P, the pressure, which once again is 0.488 atmospheres. Now, when I do my calculations using my calculator, if the number's on top, I multiply. If it's on the bottom, I divide. So, I go 0.250 times 0.0821 times 298 divided by 0.488 equals. I look to all of my measurements to see which has the fewest number of significant figures, and that's how many I must round my answer off into having. I don't look at R because it's a constant, not a measurement. So I ignore that for significant figures. But since everything else has 3 significant figures, I round my answer off into having 3 significant figures as well. So I get 12.5. As far as units, it's volume, so it's going to be liters. And the way I can tell is because moles cancel out, kelvins cancel out, atmospheres cancel out. The only thing that doesn't, liters, makes that the correct units. And now I'm done.